All right, guys, let's talk about these operations with radicals. And when I'm talking about operations, I'm talking about the addition, subtraction, multiplication, division. So let's first obviously talk about addition and subtraction, okay, of radicals. So with addition and subtraction of radicals, in order for you to add or subtract, you need like radicals. It's kind of like polynomials. In order for us to add or subtract polynomials, we needed like terms, meaning the base and the powers were the same. So same idea with like radicals, we have to have the same index and the same radicand. And you're like, well, what's the index and which is the radicand? Well, the index is where the root is, right? Which is in the wedge. And the radicand is inside the house. Okay? So that is what we're talking about. So the root has to be the same and what's inside the house has to be the same. Okay? In order for this to add or subtract. So let's show you by example here. So if I had the cube root of x squared plus 3 cube root of x squared. So if you notice that the 3 as a root is the same. And then the x squared is also the same. Okay, so since they're both the same, therefore I know that I have like radicals. All right, and we already know that just like if it was an x, there is an imaginary 1 in front of this radical. So therefore I have a 4 cube root of x squared. So again, it's very much like polynomials. We keep that radical with the same index and the same radicand, and then add or subtract the coefficient. Okay, so what if it was different? So let's say I had the cube root of x plus 3 cube root of x squared. Well, if you look at this, the index is the same, so the number in the wedge is the same. However, the radicand, the first term has x, the second term has x squared, so the radicand is different. So therefore, these two are different overall, so therefore, my answer is the same. I can't add these two radicals, so they are going to be as is, okay? So again, it's the same idea as polynomials. So although the index is the same, the radicand are not. Okay, so that will hopefully help you guys understand that. So the problem is that it's not going to be as simple as this. It's not going to always look the same, but you know, we're not in a very perfect world. So let me do a better example here. This was example 2. Let's do example 3. So example 3. So what you're going to see more of is going to be something like this. So right now it's not the same, so you can't just write it as, well, you could, but it'll be wrong. So at first glance, these are not the same. However, we can also break these down, right? So what we know is that we can see that the two indexes is a 2. So we're looking for pairs. All right, so let's break these down. All right, so what I have over here is the square root of 50 minus the square root of 98. Right? And if I was to break down 50, and let's break down 98. So what I have here is the square root of 2 times 5 times 5 minus the square root of 2 times 7 times 7. And what I'm noticing, what should I use? That should be a nice little pink. What I notice is that there's a pair of 5s here and a pair of 7s here. So that means this pair of 5 can come out, leaving me with that 2 staying inside because it has no pairs to come out to play, minus the pair of 7 can come out. And the 2 again doesn't have a pair to play. Okay, so it has to stay inside the house. So now you will notice that the index are both 2s and the radicand are both 2s. So therefore these are like terms. So therefore this is equal to negative 2 square root 2. 5 minus 7 is negative 2. And then we keep the radical the same. Okay? And let's do another example. So I wrote this down, so let's see if how that goes. I have 2 cube root. Let me try to do this better here. Let me write this down and then I'll start with a cube root of 125 minus 3 times the cube root of 320 plus 3 times the cube root of 625. Okay, so same thing. Let's break these down. So let me try to create some more room here. So let's say it's 2 times the cube root of 125 minus 3 times the cube root of 320. Oops. Oh. Plus 3 times the cube root of 625. Okay, so if that's the case, let's take a look. How do I want to do this? Let's do it right underneath it. So 125, if you do the factor tree for 125, you're going to get this. The cube root 125 is going to end up as 5 times 5 times 5 minus 3 times the cube root of, let me see here, 320, 32 and 10, 2 and 5. Well, this one I'm going to have to do that. So let me bring it over here. 320. Let's bring it over here. There we go. 32 times 10. 4 times 8. 2 times 5. 2 times 2. Times 2 times 4. Times 2 times 5. So it's going to be 2, 2, 2, 2, 2, 2, and 5. Okay? So this is going to be actually a really long one, so I'm just going to erase that off and put these down first. 2, 2, 2, 2, 2, 2. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 times 5. So I'm going to have this cube root plus, and the 625 is going to be 5 times 5 times 5 times 5. So I gotta extend this a little bit. Okay. So again, if you look at this, my index is a 3. Okay. So we're looking for groups of 3. So I have a group of 3 there. I have a group of 3 there. I have a group of 3 here. I want to use a different color here. Let's use blue. And I have a group of 3 here. Okay? So with that being said, over here I have the 2 still. My 5, I have a group of 5 that comes out. Nobody left inside the house. Minus 3. This is going to be green. So a group of 2 comes out, another group of 2 comes out. And the only one that stays in is going to be the 5 because it's got nobody there. Plus, this one has a group of 5 that comes out, and this is blue. So 5 comes out, leaving you with a cube root of, and there's that 5 that stays inside. I should have made this 5 a blue and a green. There we go. So that we can see everything. So if you already have a number that's outside the house and you're bringing something else out, what you're going to do is you're actually going to multiply those numbers. Ooh, that's what I'm missing. I forgot to bring that 3 down. Okay, so again, whatever comes outside is going to multiply what's already outside. Okay, so now I have 10, because 2 times 5 is 10, minus 3 times 2 times 2, which is 12, cube root of 5, plus 15, cube root of 5. Okay, oh look, this and this are the same. So that means my answer is going to be 10 minus, oh, actually plus 3 cube root of 5. So there goes my answer. Okay. Hopefully you have any, if you have any questions, let me know about that. All right, so hopefully everybody followed those steps there. All right. So now I'm ready to talk about multiplying. Okay, so multiplying, we're doing the same thing as polynomials. The only difference is that we might be able to reduce these down the road. So if I give you something like, what example are we on? 4 or 5. Okay, so let's say I give you a square root of 11 times square root of 3 plus square root of 7. Okay, yes, you're right. We would distribute. Okay, so what I would have is, actually, you know what I'm going to do? I'm going to make this red. All right, so therefore we have a square root of 11 times the square root of 3 plus square root of 11 times the square root of 7. And since they're all inside the house, I have square root of 33 plus the square root of 77. And if I was to try to break these down, I won't be able to. I'll get 3 times 11, which is 33, which they're both prime, so therefore that doesn't break down. And then I have 11 times 7 for 77, and those two are prime, so those two don't break down anymore either. So that is completely done, okay? So another example, well, before I do another example, here's something that you might want to remember. So you should know or remember. Okay, so if I have square root of 2 times square root of 2, a lot of you guys are gonna be like, wow, that's square root of 4. Okay, I want to start to skip that step because square root of 4 is essentially what? Just 2. So square root of 2 times square root of 2, another way of thinking about this is that I can say this is square root of 2 squared. Well, what do I know about square root and squares? They're actually opposite operations of each other, and they will actually cancel each other out. Well, another way to think about that is saying, well, I can write the square root of 2. Actually, you guys don't know that. I'm thinking the other class here. So they're opposite operations, however, so therefore they cancel each other out. So just understand that. So that's why, so in case if you see something like square root of x times square root of x, well, that's just x. Square root of 7 times square root of 7, well, that's just equal to 7, okay? So just, it's something that you want to remember. It makes things very easy. And let's say, and again, these index of these 3 is all 2, so we're looking for pairs, and this is in pairs. So if the index was to change, like let's say it was the cube root of x times the cube root of x times the cube root of x, that's also x because the index is 3, and I got 3 of them. So therefore, it would just be x that's left. All right, so that's something that you might want to know. So now it's time for our next example, which would be example 6. All right, so let's say I take the square root of 14z and multiply it by the square root of 14 minus the square root of z. Okay, so again, same thing, like you said, we would distribute, which is absolutely correct. So again, I'm going to take this and change that to red. All right. So I'm going to take the square root of 14z and multiply that by square root of 14. All right. Minus square root of 14z times square root of z. All right. So what you're going to notice is that over here on the first group here, I'm going to have square root of 14 times square root of 14. So that's just going to be 14 square root of 7. I'm sorry, not 7, z. Minus, over here I'm going to have square root of 14 times the square of z times the square of z, and square of z times square of z is just going to be z. And the 14 is going to be left alone, so that's going to be inside. These two are not like radicals. And if I was trying to break down 14, that doesn't really matter because, number one, it doesn't break down anymore. Number two, it wouldn't get me the z as a radicand. So therefore, this would be my answer. Okie dokie. Well, what's the other thing that we've learned so far in terms of polynomials? Well, you also learn something like this. Right? What does that mean? That means you write it out twice. And you would FOIL or double distribute. Me personally, I would double distribute these because it's a lot harder to see when you're foiling. So what I would tell you to do is say, okay, write it out as a double distribute. So square root of 2 times the square root of 2 minus square root of 7. Let me erase that so it looks better. Minus the square root of 7 times the square root of 2 minus the square root of 7. All right, so I'm going to do the distributing. So what I have here is square root of 2 times square root of 2. What does that give me? That gives me just plain old 2. Then, actually, you know what? Let's do this. That gives me 2. Square root of 2 times a negative square root of 7 is going to give me a negative square root of 14 because they're both inside the house. So when I multiply, I can only multiply if they're both inside the house or they're both outside the house. Okay. So over here, I have this right here, and that's going to give me a negative square root of 14 as well. And then this times this is a negative square root of 7 times a negative square root of 7, which becomes positive. And square root of 7 times square root of 7 is just going to give me 7. So what I have here is that these two are the same, and these two are the same. So what I have here is a 9 minus 2 square root of 14. So there's my answer. So they're not like radicals, so therefore I can't add them together. All right. So, is there any questions at all? Okay. So, let's now look at dividing. Radicals. Okay. Dividing radicals, we're really just going to be talking about something called rationalizing the denominator. Okay, so why are we doing this? It's because in dividing radicals, okay, we cannot have radicals. You know what? Let's just spell it out. In the denominator. Okay. So with that being said, there's two things that can happen in the denominator. We could have a monomial. Okay, so we might have something like I'll keep it simple. We could have something like this. We're at, what example are we on? 8. So we could have something like this. So essentially what I have here is square root of 144 over the square root of x. Well, square root of 144 is just 12 over the square root of x. And since here we have our issue because we can't have the radical in the denominator. So the question is, what do we do? So we think about how do we get rid of a square root, right? if I have a square root of x, what do I multiply square root of x by to get rid of the radical? Well, this is easy because the index is a 2. I need another one. So if I had square root of x times square root of x, what does that give me? Just plain old x. So that would get rid of that radical. So therefore, I'm going to multiply the top by the same thing. And when I do that, the top is going to be 12 square root of x over x. Since the radical is gone in the denominator, I'm done. And I can't reduce anything. So therefore, I am finished. Okay? Any questions on that? No? All right, example 9. So let's try something a little different. Let's say I have 3 over the square root of 28x. Okay, so here's my suggestion. I would tell you to break this down first. 28 breaks down to 2 times 2 times 7 times x. Does everybody agree? Okay, so this is what I like to say. So essentially up here, if you notice, what's in red is what I need to get rid of that radical. Okay, because I have a single x and I needed a pair of x's, I needed one more x. Okay, so here's where we have to focus. So I'm going to do this. I'm going to make a table right here. I'm going to make a better table right here. Boom. Boom. Okay. I'm going to mark this as what I have, what's given to me, and what I need. Okay. And the whole thing is that my index is a 2. Okay. So I need pairs. Right. So what do I have? I have 2 2s. I have a 7, and I have an x, right? So if I need pairs, do I have a pair of 2s? I do, I already have a pair of 2s, so I don't need any more 2s. I have a 7. How many more 7s do I need to make a pair? Do I need one more 7? And how many more x's do I need to make a pair of x's? I need another x. Does that make sense? So, if you look at this, what I would have left would be 2 times 2, 7 times 7, and x times x. So you notice I have a pair of 2s, a pair of 7s, and a pair of x's if I did this. So now, what I'm going to do is multiply this bottom by the square root of 7x. That definitely doesn't look like 7x, huh? All right. So what do I have? So the top I have 3 square root of 7x. And on the bottom, I have the square root of 2 times 2, 7 times 7, x times x. All right? Because the green is what I would multiply the black and the red with to get that. So therefore, the top, again, I have 3 times the square root of 7x over, I have a pair of 2s, a pair of 7s, and a pair of x that comes out. So therefore, my radical is gone. So that is going now to equal 3 square root of 7x all over 14x. So there is what my answer would be. This go wee. There we go. All right. So again, I break it down, what's in the denominator, and then what I do is a chart of haves and needs. Because of the index, based on the index is gonna figure out what I need. Okay, so let's do the same problem. Okay, so example 10. But instead of square root, let's do it as a cube root. Okay, so again, I would break this down as 3 over the cube root of 2 times 2 times 7 times x, which is what I have. Okay, so again, I create a table. Of haves and needs. And I said that this is based on the index being a 3, right? Actually, which I'm looking for a 3 of a kind. Okay, so what do I have? I have a 2 times 2 times 7 times x. Okay, what do I need? So I'm looking for 3 of a kind, or groups of 3. Actually, that's why I should call this. I should just call this groups of 3. Okay, so if we look at that, I have 2 2s. I need another 2 to make it a group of 3. How many more 7s do I need? Well, I only have 1 7, so I need 2 more 7s to make a group of 3 of 7s. When I have an x, I need 2 more x's to make it a group of 3. So, in other words, if I take my haves and needs and put it together, I have 2 times 2 times 2, 7 times 7 times 7, and x times x times x. Okay? So what I'm doing here is I'm multiplying this by the cube root of 2 times 7 squared times x squared. So I gotta do the same thing on top. All right. So the top is gonna be 3 times the cube root of, 2 times 7 times 7. So 7 times 7 is 49, times 2 is 98, x squared, over the cube root of 2 times 2 times 2, 7 times 7 times 7, and x times x times x. All right? So what do I have? I have 3 cube root of 98 x squared over, I have a group of a group of 2's that come out, a group of 7 that comes out, and a group of x's that come out. All right? So what do I have there? I have 3 cube root of 98 x squared over 14x. And I'm done because I can't reduce. Now again, in order for me to reduce, I can only reduce if they're both outside the house or they're both inside the house. So the x's wouldn't cancel out because the one on top is actually inside the house and the one on the bottom is outside the house. The 3 and the 14 could cancel if it was the right numbers to cancel, but 3 doesn't go into 14, so therefore I'm done. Okey doke. So this is for monomials. So let's talk about for binomials. Okay, so this would be example 11. So for binomials, this is a little different. For binomials, Number one, as I always told you, if I see binomials, I should put parentheses around it. So what do I multiply 3 minus square root 11 to get rid of that radical? So in the past, people would be like, well, let's multiply by square root 11. Well, no, if I multiply by just square root 11, if you distribute this, look at what you get, okay? You'll get 3 square root 11 minus 11. So the radical is still there, so it'd be no good, okay? So the trick of this is about conjugates. So what do we know about conjugates? Oh, conjugates is the same variables, but since the given is a subtraction, that means we will multiply by the addition, okay? So these two here are called conjugates. And whatever I multiply the bottom by, I have to multiply the top by, all right? So the top is going to be 6 times 3 plus square root 11. And the bottom is going to be what? I'm going to tell you it's 9 minus 11, okay? So you're like, but how did you get that? How was it so quick? Remember with conjugates, you guys typically say, I need to FOIL, right? If I was to FOIL this, I'll get 9 plus 3 square root 11 minus 3 square root 11 minus 11. And if you notice that these two will cross itself out. So essentially, we don't have to really FOIL. We can just, right? Remember that? Okay, because the outer and the inner would cancel each other out. So all we had to do is first and last. And square root 11 times square root 11 would be just 11. Negative times positive would be negative. All right, so this right here would equal to 6 times 3 plus square root 11 over negative 2. Ooh, look, that reduces. So it's actually going to be negative 3 times 3 plus square root 11. And there you go. There is my answer. So when I multiply the conjugate, number one, my radical goes away in the bottom. And then I just have to distribute or double distribute or FOIL on top. And if you do the conjugate, then all you have to do is flip on the bottom and you'll have your answer. All right. So with binomials, it's always going to be the conjugate. On a monomial, it's a little bit more difficult, but I think this is the easiest way of doing it because it's about making this chart of haves and needs. And if you do the haves and needs based on the index, you'll get what you need to multiply with, what you need to multiply with. All right. And then the green is a combination of multiplying the haves and needs together. All right, and that's how we get that. So that would get rid of the radical for us. And if you have any questions on the homework, feel free to let me know.